Hey guys, yeah, so let's start. Hope you had a nice lunch. So with me here is my co-founder, Jonathan Weintraub. So you're welcome. Just take a look at this guy so you know who to ask questions after the talk. Yeah, I'm going to be talking about the CryptoSat projects. By the way, we're excited to be a sponsor in this event and also have a small bounty. Which I'll talk about. So I'll explain about the technology, kind of how we came up with this idea and what we're doing currently. So yeah, let's dive into it, and welcome to ask questions afterwards. So CryptoSat is essentially a trusted party in space that serves as a root of trust for different blockchain protocols and different crypto technologies. And in terms of the mission, we essentially build satellites, like real satellites that are launched into space that power different blockchain and crypto and DeFi applications. And the mission is to provide a cryptographic root of trust that's super secure and can guarantee ultimate trust and transparency from protocols or parts of protocols that require this kind of trust. So in terms of just some of our team, there are more people involved, but in terms of the founding team, it's Jonathan and myself. Jonathan is bringing the aerospace expertise, and I'm coming from a security and cryptography background. And we have space system engineers on our team. We have people who help us work with the blockchain ecosystem. We have Omer Shlomovitz, who's the co-founder of Zengo, which is a successful company in the space of wallets and co-signatures. Just to elaborate a bit on some of the things that Jonathan has done in the past. So that's an example of one module that Jonathan has launched into the International Space Station. This box has essentially, it's growing humus in space. It's literally an experiment in space agriculture and kind of feeding plants and how you do it in an environment that's where you don't usually do this kind of stuff. So that's a super cool space project Jonathan worked on. And his probably most notable claim to fame is sending a spaceship to the moon and working on the first privately owned and operated mission to send a spaceship and land on the moon, which wasn't done by a government. So that's some of the things, and that's an image that his spaceship Bereshit took of the backside of the moon. So let's dive into what crypto satellites are and what they can provide and what they can do for the blockchain and the crypto ecosystem. So they're essentially serving as a root of trust, and it means it's a cryptographic model that's super secure, and you can be assured that the cryptographic operations that are taking place there are secure and not tampered with, and you guarantee confidentiality and transparency. So for instance, just to give an example, you can take some protocols such as Zerocache that requires some preliminary generation of cryptographic parameters to bootstrap it. Originally, you needed to do a whole ceremony that was very sensitive. Kind of, if anybody tampers with it, that can compromise the whole protocol, and it's the future of the financial system you build on top of it. So that needs to be done very carefully, and that complicates the operation. Basically, you need to bring a bunch of people to agree that everything is done correctly, that nobody has, say, physical access to the machines that are running it. So if you have a cryptographic root of trust, if you have this kind of secure environment, what's called the trusted execution environment, you can potentially do such things, such ceremonies and generation of those parameters in a completely trustworthy manner, where you can rest assured that whatever parameters were generated by this model, you can trust them and you can now start using them for your own protocol. Why is it tamper-proof? Well, that's pretty simple. That's because it's in space. So we need to take care of supply chain concerns on Earth and kind of trustworthy integration of the satellite. But since the moment you launch it, nobody can access it. You might have seen in a lot of movies that things are docking in space and captured in space. That's kind of a sci-fi today. The most that can be done today is potentially taking down a satellite, which is something like a nation state can do, but not beyond that. We don't really have the technology to just capture a satellite and do anything to it in space. And on top of it, everything is monitored. There are a couple of independent agencies run by the US, Russia, China, different countries that are not colluding with each other, and all the skies are monitored, so you can see very small objects approaching your satellites. So every attempt to tamper with such a satellite would be noticed pretty easily. In terms of transparency, that's also an interesting property, and that basically means that the satellite communication to Earth can either be encrypted, but it can also be open. So for instance, if we want to announce some parameters or to generate something that multiple parties need to agree on, if it's broadcasted by satellite, you don't have kind of a split view of the world. It's compared to something that goes over the terrestrial network. So multiple different ground stations can receive the signal and gossip between them and agree that they're seeing the same thing. So for instance, if there is something like a dispute over the latest state of a certain blockchain, that's something that such technology can help with, potentially broadcasting, say, the most recent block's hash, and having everybody receive that and see that that's kind of the most recent state of a certain blockchain. And that can be useful for various protocols. And finally, what enables this to be actually usable and practical is a fairly low cost of launching those satellites due to the advancements of the satellite technology in the past decade. And what we're looking into is using what's called the CubeSats, so small satellites. And you can see like this little coin next to it. So it's essentially this little box, but it's a fully functional satellite that is powered by solar energy. It can run computations, so like a fully functional satellite that can power those applications. So they're miniature and they're fairly low cost to assemble and launch. Can be built with fairly off-the-shelf commercial hardware. Obviously, that's very well tested to operate under space conditions and cosmic radiation, but still pretty standard hardware. So that enables it to make it pretty affordable. And then we can have a constellation that has multiple of those. So just kind of going deeper into that, that's an example of how such a CubeSat looks from the inside. So it's essentially this enclosure, this cube that has a couple of boards. One of them is an onboard computer that does all the operations. That can be something like a standard ARM processor. On top of that, we also have, we're developing a cryptographic random number generator that essentially provides true randomness. It basically harvests radiation events that are truly unpredictable and provides a true source of entropy for things like generating keys, generating different cryptographic parameters. And I'll talk about one of the applications of that for blockchains. So in terms of some of the use cases we're working on and some of the collaboration with the ecosystem, so we have a few partners and first customers that we're working with on different use cases, all related to having this trusted party in space. So Veles is a nice example of using CryptoSat as a trustworthy source of entropy. We essentially provide an oracle where we feed the VRF into the Veles blockchain. So that's in the workings. We just announced the partnerships and starting to work on that. And essentially, we provide this random stream of bits that is signed, digitally signed by the satellite. And then if you're using it from within a blockchain, like Ethereum or Solana or anything else, you can basically verify. You can use the CryptoSat public key to verify that you have those random bits that are coming from an authentic source of entropy, which is CryptoSat in this case. And then you can use it to do all kinds of things, running lotteries, generating cryptographic parameters, yeah, whatever you use randomness for. Protocol Labs is an interesting one where we're working on something called the verifiable delay function. So verifiable delay functions is a whole area of research that started a couple of years ago, and its goal is to provide a guarantee that a certain amount of time has passed. So that sounds kind of simple and kind of weird. OK, what's the problem with that? But within blockchains, which are its own isolated kind of system, its own virtual world, you don't have this notion of time. In something like Ethereum, you don't internally have a notion of how much time has passed. So for instance, if you want to have something like a smart contract that tells you to move, tells the program to move funds from one wallet to another after, say, a week has passed, there might be incentives for attackers to lie about how much time has passed and immediately say that a week has passed and you need to move the funds. So there needs to be some way to know how much physical time in the physical reality has actually passed. And for that, you need those external oracles. And there might be incentives for attackers to take over servers that provides those kind of oracles. So a very trustworthy source of time, for instance, can be useful. So we're working on this verifiable delay function, something that provides that kind of oracle and is based on physical constraints. There are kind of naive approaches based on just running a clock in the satellite and providing signed timestamps. But there are more complex approaches that require less trust in the actual software, and they're based on physical constraints with communicating with the satellite. So you can only communicate the fastest you can communicate depends on the speed of light, right? So that's like a minimal bound on how long it would take to do a round trip to a satellite and back. And based on this physical property, we essentially are working on a construction that combines cryptography and those physical properties to provide those minimal bounds for how much time has passed. So building on top of that, we can provide those kind of oracles. And then another example of where a trusted party can be useful is something like co-signing or threshold signing. So there are different wallet projects that are based on distributing trust between multiple parties using MPC or threshold signatures, where, say, the company that provides the wallet service has one part of the key, and then the user has another part, and potentially we want another party that's very trustworthy and tamper-proof to co-sign a transaction before it's approved. So that's where CryptoSat is coming in to be a cosigner, essentially a consigner that is very hard to compromise, and without its participation in the protocol, you cannot sign a transaction. So that kind of secures very high-stake transactions. So yeah, I kind of pretty much talked about those different use cases, so we can go over the slide very quickly. So as I mentioned, random beacons are one use case, verifiable delays. Then the last one is trusted setup and ceremonies. So as I mentioned, all this generation of trusted parameters is something that often protocols or infrastructure incur. If you're thinking about things like ZK snarks and zero knowledge proofs that are starting to gain a lot of traction for different use cases, those often require setups that need to be trusted. So you need to generate something that's called a common reference string, CRS, to often spin up a snark scheme. If you're familiar with Stark or snarks, so Starks are trustless setups, and snarks often require this trusted party to generate some parameters to start using the scheme. So that's exactly an example of a ceremony where such a party can be useful. So that's another use case we're exploring. I want to dive a bit more into the architecture of the random beacon, of the random or kind of verifiable random oracle, the use case we're exploring with Velas. So essentially what happens here in terms of the architecture, we provide a couple of things. We provide, first of all, the trustworthy source of entropy in space that kind of harvests the entropy and provides a random stream of bits signed by the satellite. And then CryptoSat also provides the ground infrastructure for feeding that into the blockchain. So in order for you to start to be able to use it from within actual smart contracts in something like Ethereum or any other platform, you need a way to essentially access this randomness from within those smart contracts. So what we're going to create for that, and that's something we're working on now, is essentially taking this random beacon that we're getting from space and creating a smart contract that somebody can integrate with inside the blockchain. So we're essentially constantly updating this smart contract with those new values, with this new entropy. And then you can call a function. You can call like a getter function from within another contract to access this randomness. And what you need to do is you need to use the public key of CryptoSat to just run a verification that this randomness is coming from a trusted source. So that's how such an oracle would look like in terms of the architecture. I want to talk about a couple of things that we did recently in terms of experimentation and where we are with building this infrastructure. So we're currently working on our first satellite and are hoping to launch it soon. Basically, hoping to have it operational by the end of this summer. But in the meantime, we started experimenting with operations that involve space and exploring some use cases around it. And we partnered with a couple of companies and organizations to do that. So recently, just last month, we ran an experiment aboard the International Space Station, where we uploaded our code and were communicating with the different programs we were running there. So one example was DRAND. DRAND is a project developed by something called the League of Entropies. So that's like a consortium of multiple companies and universities that includes Cloudflare, Zengo, EPFL in Switzerland. Basically, multiple Protocol Labs is another participant, and they're very involved in developing DRAND. So that's essentially a distributed randomness beacon where multiple parties contribute entropy to ensure that even if you compromise some of those parties, the random beacon, the randomness you get at the end from this protocol is still trustworthy as long as there are some trustworthy parties participating. And our goal is to essentially join this consortium, kind of provide another trusted party that would contribute to this random beacon. So essentially, the experiment involved running two nodes, one on Earth and one in space, to generate randomness together and run the DRAND protocol. And that essentially simulates how it would work with an actual satellite. Another one was signing actual, kind of doing a threshold signature for an actual Bitcoin transaction. So that's an experiment that we did with Zengo. They basically provide this threshold wallet that enables multiple cosigners to approve a transaction. And we actually signed a real Bitcoin transaction that we could take afterwards and post on the blockchain, compatible with Bitcoin. Another cute experiment we did is enabling people to have their messages, kind of whatever data, signed in space. So we created this tweets from space campaign where we had people tweet at us, tweet at CryptoSat bot, mention us, and then we would pull automatically all those tweets and have those messages uploaded to the space to the International Space Station, have them signed there with a key that never leaves the space station, and kind of simulates how it would work with an actual satellite. And then we reposted it back on people's Twitter walls. So that was a nice experiment, and people were kind of really raving about this and posting all kind of messages that CryptoSat would sign for them. So that's the Tweets from Space campaign. So in terms of onboarding use cases and starting to work with developers, that's something we started developing pretty early because we realized we want to move forward with use cases and start onboarding developers in the ecosystem, even prior to working with the actual satellite. And for that, we created the CryptoSat simulator. So you can actually see it on simulator.cryptosat.io. You can see it online, play with it a bit. And what it has, it's essentially an interactive tutorial that also has a simulation of the satellite trajectory and its connection to different ground stations on Earth. And a sample API that enables you to explore how you can interact with such a satellite. So for instance, here on the left, we see an example of creating a request. And then on the right, you can go through different use cases, different little tutorials that show you how to sign some data using CryptoSat and what the API looks like. And also can explore how you work with latency constraints and the fact that the satellite is sometimes connecting to some ground station, then connecting to different ones, or sometimes it's out of reach, and you need to wait for the request to complete. So essentially, this is like a useful simulation to start exploring, and you can implement small use case using this simulator, and then actually have it kind of be ported to working with an actual satellite once we launch one. We actually run a bounty around that. So we have this small 1K bounty that we offer for improving the satellite and coming up with your own use cases that you'd like to contribute. So you're welcome to check out the online simulator and also fork the repository. You can take a photo of the slide and go to this link. We have a Discord channel, so if you have any trouble following the instruction there, you can ping us and we'll help you run the simulator locally. And then you can potentially create a pull request and contribute a new use case for how such a trusted party can be used for some application that you're thinking about. So there are some links. Welcome to take a photo of that if you want. There are some links to the relevant repository and the dependencies for the CryptoSat simulator. Yeah, so that's pretty much what we wanted to tell about CryptoSat. And also wanted to share that we're hiring. We're expanding our software team, so looking for a software team lead, looking for a cryptography engineer, and for a full stack developer to work on the various things, including both the space segment software and the ground infrastructure that we're building for that. So welcome to email us at careers.cryptosat.io. And that's pretty much it. Welcome to approach us, talk to us, ask any questions about that, and check out those resources about CryptoSat. Thank you. Yeah, so we've got some time left, so happy to take questions. Yep. Mm-hmm.
So with these CubeSats that are small, you said they're about the size of a coffee cup. Are there any issues with like relaying the information that it produces from space for performance around? Like what are the logistics of that?
Mm-hmm. Jonathan will be able to. Maybe Jonathan will take it. Yeah.
So the question was around the logistic of relaying the information from a coffee mug-sized satellite all the way to the ground. So it was actually a revolution in this field quite recently, and the entire industry became commoditized. Not only on the satellite side, which you actually can go online and buy the components and assemble it in your home, but also on the ground station side. So now you can go on AWS and rent a ground station and communicate with your satellite. So this kind of revolution in the infrastructure is what's enabling us to build this so cheap, because you don't have to set up a ground station in your backyard. You can actually rent one.
So the data feed from this CubeSat would be like completely like uninterrupted through its orbit around the Earth.
So you get really good coverage. Obviously, over the Atlantic, it's a little more difficult to get ground stations, but for the most part, you get pretty good coverage. Especially if you have multiple satellites, you're going to have at least one in line of sight. Yeah. Was another question there? There's also another thing. Yeah, go ahead.
Yeah, how can I verify that I'm talking to a satellite and not just someone else's computer in an Amazon data center?
That's a great question. Jan, you want to take it? Yeah.
I'll talk a bit about that. Yeah, by the way, just to address like the previous question a bit more, essentially one of the things we're building, and that's kind of, you don't see a lot of it in the space industry, is essentially convenient API, like RESTful APIs to access this stuff, so you don't need to deal with the complexities of talking to satellites, and what enables us to do that, as Jonathan mentioned, is some improvements in the ground station infrastructure. If you kind of look at the simulator, you're also able to see how you deal with requests and their latency. So you kind of poll on them. You see that the request is completed because the satellite might not have a line of sight at some point. So then you kind of poll on that and see when it's ready, and then you receive it back. To this question, yeah. So essentially, I was mentioning the CryptoSat public key multiple times. The way the operation will start is essentially with some ceremony, kind of a one-time ceremony that we'll have to do for each satellite we launch, where the satellite generates a keeper once it's in space. Once it's in orbit, it will generate a keeper, and then it will start broadcasting a public key for a while. So essentially what we have at this point is a ceremony that involves both CryptoSat, but also like independent parties that will have to kind of gossip and announce that they see a certain public key. That will be published, and that needs to be kind of that needs to be incorporated into your code and used to verify any request, any response that's coming from the satellite. So essentially, every command you send, you don't need to really trust neither the CryptoSat infrastructure nor any kind of computers along the way. We're just going to be relaying the requests, and they are going to be signed by you, and you're going to have a signed response from CryptoSat that you're going to verify with this public key. But yeah, this is like a point that's a bit sensitive in the sense that we need the ceremony where we publish the public key, make it visible to anyone, and that's like an initial period of time during which the satellite doesn't start yet handling requests, it just broadcasts the public key. Yep.
To follow up on that question, so if the key pair is generated in space and it starts broadcasting the public key, how do you know that the public key being broadcast? Like, what's the communication channel? Is there integrity on the communication channel where it's publishing?
Yeah, Jonathan.
So you can also, if you want to, and you're extremely paranoid, you can set up a ground station in your backyard. It's actually not that expensive, and you would know to get that information directly from the satellite if you want to verify that. So there are actually a network of what they call amateur radio operators that they do this for fun. They communicate with satellites. So you can just get the public key directly from them, and you know where the antenna is pointing at.
So I'm not too familiar with like GPS communication or in that sense, but like, is it fairly trustworthy to say that the signal is coming from this location in space? What's the risk of it coming from a different satellite?
Yeah, that's a fair question. So how do you know that you come on for that particular satellite and not someone that is flying by? And you can do it over time, right? The satellite has a predefined orbit around the Earth, and if you do it from multiple parties around the world, then only the satellite was crossing all those points is able to fulfill it in the right times and the right place. So it becomes a very, very difficult attack to match your transmissions directly with a specific satellite that is out there. And if you do so, there's actually a global monitoring network that will tell you, actually, there's another satellite that is really in your orbit, and we would know that we've been compromised if that happens. If that makes sense, yeah. I do want to say, I think we are out of time, but one of the advantages of launching stuff to space is you get to put whatever you want there. And one of the things that we can do here with the audience, if you want, is we can take a picture and just put it in a satellite, so you're going to have your face in outer space as for future generations to enjoy. Is that something you want to do? Is that, yeah? Yeah, okay. All right, so we're going to do this with the selfie camera here. And that's the camera here. It's going to be up here, so make sure you see the camera, because this works two ways. If your camera cannot see you, you cannot see the camera. And we'll take a selfie and put it on a spacecraft. Please stay tuned. June 2022 is the launch date, so you know that your face is going to space, all right? Are you guys ready? On the count of 3, everybody say space, all right? All right. I think I'll do it in 2 pieces because it's going to be hard to get everybody in. So shout space on the count of 3. 1, 2, 3, space! All right, now you guys. 1, 2, 3, space! The first ones were better, I know that. All right, thanks you very much, folks.